I'm going to speak about 3D reconstruction of deformable surfaces from an monocular video and using mostly geometric cues, a bit of deep learning still, as you'll see. And so I'm leading a research group which is named ENCO, that means endoscopy and computer vision. So we do computer vision with the as targets mainly computer-assisted surgery. So that's what we have in the background for our developed theories and systems. And so I'll talk about the methods and then show application in computer-guided surgery at the end of my talk, and you'll see how it's used on concrete examples. Right. So 3D reconstruction, as you know, which is also called inverse imaging, is about the task of converting several 2D images to a 3D model of the observed object or environment. So with pictures, we have a camera that films or take photographs of the environment. We can access digital images taken from this camera, and we reconstruct a model of the environment, which can be a point cloud, something very simple, and a model of the camera at the different time instance where it took the different pictures. And of course, this is just a mathematical model. This is not reality, and we can make the scene structure more complex by adding to the point cloud things like the topology, using the mesh, so which codes for the relationship between the different observed points. We can encode the appearance with a texture map. We can make it smooth to be able to access differential properties, and we can even complexify it even further. I will use differentiability a lot in this presentation, and also the appearance to be able to match the models to each other through the images and across images. So there are mainly two approaches nowadays to reconstruction. Of course, the learning-based approach is gaining popularity. The idea is to learn the reconstruction function directly from data, and so we have this huge function represented by a network that maps the image data directly to the model of the reconstruction, so to the structure on the cameras. And by doing this, we sort of avoid the analysis, the explicit analysis of the images and the what we call the visual cues that they contain. These visual cues, they are these cues from the images that tell us something about the 3D content which is observed in the images. So here, with this approach, everything is contained implicitly into the weights of the network. But the other approach, which is older somehow, and which has been also used very successfully, which we could call the physics-based approach, is based on analysis, explicit analysis of the visual cues. And typically nowadays, this would be called the handcrafted approach, where we search the images for visual cues that tell us something about 3D. And probably one of the most successful visual cues is the visual motion. So where we observe the primitives, the motion of geometric primitives across images. Um, and from this motion, we can infer 3D. And other well-known and successful visual cues are the shading, the occlusions, the blur, the silhouette, and the shadows, and there are more of them, probably more exotic, but these are the main ones. So I'm going to discuss this physics-based approach to 3D reconstruction mostly in this presentation, in the case where we have deformations. Classically, this has been studied a lot with the assumptions of rigidity. So this is the one-on structural motion approach, where if we can take multiple images of a rigid structure, something that doesn't change through time, we then have access to a whole theory, the theory of visual geometry, and its computational implementation, which is structural motion and SLAM to some extent, visual SLAM, and which is a very mature technology nowadays. So you can see an example from the literature on the right side of the screen. So I'm going to discuss this in the case where what we observe is not something which is rigid, something that doesn't change. It is something that evolves through time. And a very simple example, which I'm showing here, is a piece of paper which is deformed. And we take several images of this piece of paper. And so the shape is never the same um, through the images. So rather than searching for one shape as in structural motion, we here search for several shapes, one shape per image, and we have to recover all these shapes. So if we have n images, we have to find n shapes, still combining the visual cues from the n images. And I'm going to take the physics-based approach, and I'm going to use the visual motion approach. So that forms quite a recent problem compared to either the rigid structural motion and the other traditional visual cues from visions. And the main question we have to address here is how can we combine the different images, what priors we can exploit to replace somehow this very strong rigidity prior used in structural motion. So there are several types of such priors we can use, and the first one, which is a very natural one, is to put priors on the shape we want to reconstruct. And a natural one is the smoothness, of course, that the shape, if you look at one point on the shape, the other points close to it will be also close in space. And we can implement this mathematically with a constraint on the smoothness of the model that represents the shape. There are other possible constraints, of course, and I'm going to stick to smoothness for this discussion. Then there are priors we can put on the deformation that occurs in time across the different shapes, across the different observations. And I'm going to exploit smoothness and another important one, which is isometry and approximations of isometry, such as quasi-isometry, that tells us that when there is a deformation occurring to the surface, then the points stick together. If they're neighbors, they'll move together in space through time. And finally, there is a very important prior that we cannot always exploit, but sometimes we can. You'll see that in the medical application that I'll discuss, we can sort of exploit this template prior. And this prior tells us that we can have access to a model of the object in some reference configuration. And typically, reconstruction can consist of deforming this reference shape towards the target shape given the image data to guide the deformation. So in this case, when we have a template, the problem is called shape from template, the reconstruction problem. And there is an important result from the literature, which says that it's solvable from a single image only. I'll go through the details of why this holds. But the problem setup is this one, the one you can see on the screen. So you have a template. Again, this is the object we're interested in. Here, this piece of paper in some reference shape. Here, it's an easy case because the paper can be physically flattened. So as template, we can just take a flat plane. And the shape from template, the SFT process, takes this template and an input image and can output the 3D reconstruction of the object as seen from this input image. So the ability to solve from a single image only is a very nice property because it means we can solve in real time without relying on past images, past observations, and so we don't need tracking and these sorts of things to be able to recover from failure, for instance. So that's a nice property. In practice, the template is available from either a digital object model, which is a very common case. For instance, if you have a CAD model and if you 3D print the object, then of course you have the object model from the start. But other possibilities could be to scan the object using structural motion or structured light scanning if you just have access to the physical object, and then you can recover the template model to be used in SFT. This video shows an example of what we can achieve with the current state of the art in SFT. what you can see on the top is the digital model of this juice bottle, which was actually reconstructed from a 3D scanner. And these three sets in the video on the bottom of the screen show the input image from the left to the right, the input image, the computed depth map, and the textured 3D reconstruction on the right. So this runs in real time. This is joint work with my colleague Toby Collins. And as you can see here, we have access to this live 3D reconstruction. And it's not just the computation of a depth map, we have a completion mechanism for the hidden parts of the object. So if you look right now on the right of the screen, we can visualize the back of the objects, even though we never observe it in the actual image, which is because we sort of register the 3D model to the actual image. So we deform the whole model towards the actual image, and even the hidden parts are recovered in this process. In these results I'm showing, there is no deep learning. This is entirely based on modeling and physics-based reasoning. So the second case of 3D reconstruction, which is also very important, is the case where we don't have access to a template of the object. It could be, for instance, where we don't have prior information on the object, like we discover the object at runtime only, or in the case where the template is not constructible easily. So in this case, if we want to be able to do 3D reconstruction, we have to use multiple images, as in this example. So here we have three images of a piece of paper, and we're able, with this algorithm, to reconstruct the three observed 3D shapes. This is a very direct extension of structural motion to the deformable case, to the non-rigid case, and it's been called in the literature non-rigid structural motion, NRSFM. And we have been able to prove that it's solvable from at least two images, even though with two images only, we still have ambiguities that remain, but there are discrete ambiguities in the general case, and I will give you some details about it. This is not a technology nowadays, but the research is quite advanced and there are solid theoretical results on what we can obtain from several images. So this is the layout of the rest of the presentation. I'm going to discuss shape from template. So this example where we have a template and just one image as input from which we do reconstruction. Then the classical non-rigid structural motion. By classical, I mean non-deep learning approaches, so with physics-based reasoning. Then I'm going to discuss briefly a recent solution we came up with for the SFT problem using deep learning, which we call deep SFT. And finally, the application of these technologies to laparoscopy, which is a form of minimal invasive surgery. So we start with this SFT problem. So we have the template, the input image, still for an example on a piece of paper, and we want to do reconstruction on this piece of paper. And this is how the classical pipeline looks like. So we first match the input image to the template. For that, we use key point correspondences. Here I'm showing shift correspondences. Of course, there are miscorrespondences because this is based on local comparison in descriptor space. And of course, since several points look alike, there may be mismatches. So we have a local consistency check of these correspondences. Basically, we look at the correspondences and the neighboring points, and if they don't agree in terms of the displacement they have across from the template to the image, we sort of discard them because this indicates that they must be miscorrespondences. This removes a lot of miscorrespondences, not all of them, but a lot of them. So we have quite clean data from there. The next part is to do 3D reconstruction from there. But before that, we have a critical step, which is to upgrade these point correspondences to what's called ACEs, affine correspondences. So for that, we basically upgrade each point with its local differential structure represented by an affine transform. This affine transform, this encapsulates the local behavior of the optical flow basically between the template and the image. This is like the first order expansion of the optical flow around each point and can be represented by an ellipse on the images. So if you look at the content of the ellipses drawn on these two images, you can see by close inspection that the content is approximately the same. This upgrade is very important because, as we'll show, there is a computational procedure that can reconstruct each affine correspondence completely independently to 3D. And this is very important for robustness because it means we can do local 3D reconstruction without relying on the other correspondences, which of course may be wrong because of the matching process. So this is important because if you're familiar with structure for motion, you know that in structure for motion, a very essential component is the ability to do random sampling with RANSAC, for instance, to be able to be highly robust to mismatches. And the ability to do RANSAC is because we have global motion models for the whole image, like the fundamental matrix, the projection matrix, the trifocal tensor, etc. In the deformable case, all this breaks down completely. So the ability to be able to do robust reconstruction here involves being able to do very local reconstruction. So to be able to reconstruct from just one point. And I'm going to now discuss this, the theoretical foundation of how it's possible to do this very local reconstruction, this shape inference process. So I'm going to present this one-point reconstruction theory very briefly by giving an algebraic derivation. If you're interested in the details, this is of course provided in the papers, and this is based on Riemannian geometry. And then I'll speak about the extension of these to non-rigid structural motion. So when we have one point correspondence with the affine region around it across multiple images, but we don't have the template anymore. So in the case of SFT, we first have to start with the geometric model of the problem. So here we have the template on the left. Of course, the template here is a 2D template because the paper is something we can physically flatten, but the approach I'm presenting is trivially extendable to 3D objects, the ones we cannot flatten physically. On the right, you have the input image on the bottom, and on the top, we have the unknown surface that we want to reconstruct. So we're going to assume this surface is differentiable. Actually, we assume it's smooth, but we just need it to be twice differentiable. And we have this operator, capital Pi, which is the projection operator that takes a point in space in camera coordinates and projects it to the image space. And this is equivalent to just knowing the intrinsic parameters of the camera. So you can take this one for granted. In this figure, everything which is green is known. And so the arrow that goes between the template and the image represents the fact that we know the affine correspondences from the pipeline I've presented. And everything that is blue, the dark blue, is the part that are known and that we want to compute, in particular this 3D surface. So we start with this PQ point coordinates. So you can take these as the 2D coordinates of a point in the template and in the input images. Here, we're not using the affine part of the correspondence from the start. We'll introduce it shortly, but I just want to show you that if we don't use it, of course, the problem cannot be resolved. So we state our problem, find the 3D point capital Q in the 3D space, given the correspondence P to Q and the projection function capital Pi. So our constraints is that if we take the 3D point and we project it to the image, of course, it lands exactly on the observed image point, small q. So capital Pi applied to capital Q is small q. So can we solve this? Of course, we have to count simply the number of unknowns. We have x, y, z for the 3D points, and two constraints, which are the x, y constraints in the image, and of course, it's under constraints. We're short of one constraint, so that's an obvious reasoning. So let's build up with more constraints. We now introduce these local neighborhoods, as you can see with the small green circle in the templates, and introduce the fact that when we embed this template to the 3D surface, this local neighborhood should be preserved. That's this isometry constraint I was mentioning as prior at the start of the presentation. The isometry just means that we don't have local extension around the points on the surface. This is a very natural and ubiquitous constraint. It applies to many objects under regular usage, like cloth, skin, paper, of course, and the organs that we observe in surgery in particular. So in my case, this is what I'll be interested in. So this is a very strong constraint. It's somehow like the equivalent of a local rigidity. And mathematically, it's translated by the fact that the first fundamental form, which is also called the structure tensor, is preserved between the templates and the shape that the unknown shape we're trying to recover for 3D reconstruction. And armed with this new constraint, we can ask again whether we can solve the problem. So still, now we have 9 unknowns, not 3, because the local structure around the 3D point becomes an unknown in the problem, and it has 6 parameters. And the new constraints for isometry we have introduced just actually provide 3 constraints: preservation of the structure tensor. So we're still short of 4 constraints. That's even worse than it was with the previous model. So we keep enrich this problem formulation with more constraints. Now, what we introduce is this ellipse here in the input image, which represents this affine correspondence I was discussing in the pipeline. Once we have this ellipse, actually, we can enforce the fact that the local structure on the 3D surface projects to this observed ellipse here. And this projection is here, given as our third equation in the system. And it's basically dependent on the first order derivative of the camera operator, which we can trivially compute because the camera is known. But the good news once we have this is we still have 9 unknowns, but now we also have 9 constraints if we add up all of them. So the system is consistent. It has nine unknowns, 9 constraints, and we can really wonder whether it's solvable uniquely. So we analyze the nature of the constraints for that. So the first constraint, the reprojection at 0th order, is linear. The second one is quadratic because we're multiplying unknowns with each other. And the last one, if we write it explicitly for the perspective camera, is quadratic as well. So A, this system is a quadratic algebraic system. Everything is polynomial here. So if we compute the theoretical bound on the number of solutions, it's quite high actually, 128. So it's too high for these general solutions to be interesting. However, the good news is that there is a single solution for the 3D point coordinates and only 2 solutions for the local differential structure around this point. Actually, if you're familiar with post-computation for 3 points, this system represents some sort of infinitesimal P3P system when we take the 3 points we're interested in very close to each other, infinitesimally close. So this is a good news, and also there is a very simple analytic solution to this system. So if one day you're interested in solving point reconstruction from a single point and the local first order differential structure that you can obtain from optical flow or local registration, there is a very simple solution to that for which you can find MATLAB code on my webpage, for instance. And so this is really good news. So in practice, for 1 point and the local differential correspondence, we can find the 3D point, so the depth, and we find two possible normals of the surface around this point. So this correspondence is a first order differential correspondence. It's affine correspondence, and we can compute it very simply with at least three different ways. One is to detect and match affine covariant key points. The other possibility is to compute optic flow and just keep the optic flow around this correspondence. And the third possibility is to use an image warp function that we fit to key point correspondences. So I'm showing how it goes for this warp function. Here, this is a thin plate spline that we have fitted between the template and the image, and we represent by this red grid. So if we fit this thin plate spline, we have access to the this affine correspondences very easily. So that's an example of reconstruction results obtained with this method. You can see the input image, and the grid you can see on the input image, which is superimposed, was obtained by fitting a thin plate spline. So this works automatically from SIFT correspondences. And on the right, you can see the 3D reconstruction we obtained. So here you can see another example, which is reconstructing a balloon. The template is shown on the top and the input image on the right, and the reconstruction on the left. So remember, this is a process that goes independently for each image. So there is no notion of failing because each image is processed completely independently. And this framework, SFT, has been extended in a number of ways, of course, to 3D templates. We have used it as well to calibrate the camera online, so we are able to compute the focal length. We're able to handle more advanced deformations than isometry. So conformal deformation, which preserve not length but angles. This is a weaker assumption. Equiareal deformations, which preserve local areas, so it's even weaker. We're able to handle affine cameras and also 1D structures. So you can see an example here. We have reconstructed the shape of the road sign just from a very simple template, knowing that the points were equally spread on the floor, and we were able to reconstruct the shape of the road just from this knowledge by defining a trivial template. So you can see the reconstruction of this white line on the right of the screen, and this is quite accurate. So I'll skip this part and discuss now the case of non-rigid structural motion, which is, remember, this case where we don't have a template. Of course, it's a more complex case because we have a much weaker knowledge on the structure of the scene that we want to reconstruct, and it's a real question on about whether we can actually do local reconstruction in this case. And I'll give a very brief derivation of what we have just to give you a feeling of how we can obtain and what's the main result. So this is joint work with Shefali Parashar during her PhD thesis in my group. So we started from this very simple modeling. We have two images. I'm not going to consider more for this simple derivation. We know the camera operator for these two images. Everything is done in camera coordinates, so we assume that we have a local camera for each different frames, and we're interested in recovering the 3D structure, which again is different for each image because the object deforms across the images. So this is our model, and we start, as in the case of shape from template, by a simple point correspondence between the two images. And we start modeling. So for these 2 points, we have a non-3D points on the 3D surface, and we want to find their coordinates given the correspondence and the projection operator capital pi, as in the structural motion case. So we introduce two constraints, which are, of course, that the 3D points must project at the right location in the two images. So we have these two constraints, and we can start counting the number of unknowns and number of constraints to see if we can decently think about solving this. So of course we have two 3D points as unknowns. So we have six unknowns in total, 2 times x, y, z, and we have only 4 constraints because one reprojection is only 2 constraints in a single image. So of course the overall system is under constraints, and we cannot solve it uniquely. So we keep on modeling, and we introduce the local differential structure around the points. The aim of introducing this, of course, is to be able to model something on the deformation of the objects with isometry. And we introduce the local area in the first image to be able to reason about this local structure. So the further constraints we have are the third one here in the system, which is isometry, which just says, as in SFT, that there is no local extension around the point, and that if we project this local structure around the point, it projects to the image in the canonical observed structure into this image. So if we count the number of unknowns, we have 18, and we have 11 constraints in total. So we're short of 7 constraints, so obviously we still can't solve. So we keep modeling and adding constraints. We introduce the local differential structure in the second image, is AQ2 around the second point, and we introduce the constraint that the corresponding 3D local differential structure projects to this one in the image. So now we can count 18 unknowns, 15 constraints, so we can still not solve. And actually, we're a bit doomed here because we have published a couple of years ago a theorem that says that if we keep trying to analyze things here with only first order, so differential first order constraints, no matter the amount of images that we can add to the system, no matter the amount of points we can add, we cannot solve locally for the 3D structure. There will always be more unknowns than constraints. So the way to go is to add orders, actually, to differentiate the surface more than that. And so it means like looking a bit further around the point on the surface. So the main result, like I was saying, is that at 0th order and 1st order, this is always under constraints, no matter how we put things. But a strong result we obtained is if we go to 2nd order, then it starts to be well constraints, and we can start solving locally. And we have shown that the 2nd order system, A2, can be reduced with some manipulations to 2 cubics in 2 variables that we could solve quite easily and quite stably. So this is quite a strong result because it means that we can solve for 3D reconstruction very locally. So I'm going to skip the details and show you results of how it works. Here you can see this hand, a video of this hand bending, and on the right hand side the point cloud that we obtained for this hand, superimposed with ground truth in blue for the last frame. So we obtained this ground truth just for the last frame because we had to use another sensor for it. You can see the video again. And another results just for 5 frames here. So this was shot by another research group from CV Lab, and with the Kinect, so we had access for this data to some ground truth, and we could measure the error of non-rigid structural motion here, which was quite reasonable, being lower than a centimeter. So we have done extensions to this. We also proved that we could compute the focal length of the camera, that we could handle weaker deformation models than isometry, so conformity and equireality, as in the shape from template case. But we also shown that with the affine camera, we couldn't locally reconstruct anything. So that's the takeaway message for both SFT, so the case with the template, and then NRSFM, the case without the template. If we make the assumption that the surface deforms isometrically, then in the case of SFT, we can solve from just one correspondence if we have the local affine structure at first order, which is quite simple to obtain from the image data. In the case of NRSFM, we have proved that we cannot solve at first order, no matter the number of images we use. However, we can solve as soon as we go to second order from at least 3 images with very mild ambiguities, actually. In general, we just obtain 3 valid solutions that we can very simply discard 2 of these solutions and keep the correct one. And from these, we can actually embed these solutions to robust and automatic optimization engine that can provide NRSFM solutions from input images. So the next point I want to discuss is actually an attempt we've made recently. This is joint work with colleagues from the University of Alcalá, and we have tried to solve SFT from a deep learning approach. So the pipeline is this one. We have as inputs an image, and we train a network, here this main block, to be able to infer the depth of this object, but also the registration of the object to a given geometric model of the object. And we tried it with a very naive approach, and it didn't work really well. So we had to add some refinement blocks. One is the depth refinement block, and the second one is the registration refinement block, and train the whole thing. And to add as well a post-processing to be able to obtain the whole shape of the object and recover the hidden parts, not just the depth of the visible part, but also the hidden parts. And for that, we used a handcrafted approach with an as rigid as possible definition of the model constrained by the output depth from the network. So technically, we have a fixed image output. We have blocks based on the ResNet 50. And what's important is that this is trained for a specific object, right? So this works just for one object and not is not object agnostic. So we have to train as many times as the number of objects we want to be able to process. However, a strong point that we improved on compared to previous work is that we can adapt to new camera intrinsics. So we don't have to train from images which were captured with the same intrinsics as for the camera, which is used at runtime. So this opens the scope of this quite widely, actually. We trained from synthetic data, which we could generate because, remember, this is shaped from template. So we have the template, which is an object model, which we load it with Blender, and with random backgrounds, we could generate a lot of data. Of course, the domain is different from the actual domain on the real images. So we had to use real images that we actually filmed with a Kinect, so we have access to the ground truth for the labels on the depth. Of course, we don't have access to labels on the registration because we have no means of tracking the position of each point on the object with respect to the template. And this is the way we trained our system with this data. So the last block, this as rigid as possible, is a physics-based approach, so it's not trainable. Then we had a first training step for the overall thing, which we trained in a supervised manner with classical loss functions, just from our synthetic data set. This is quite trivial. Then we fine-tuned the refinement block for the depth, and for this, remember, we had this Kinect data with ground truth on the depth, so we could do supervised refinements with this real data. This improves actually the performance quite a lot, and also we found that using a prior, a TV total variation L1 prior on the depth improved also the performance quite substantially. Then we had a refinement as our third training step of the registration block, which was self-supervised because we don't have access to real labels on all of the registration. So what we did was to minimize the photometric error between the input image and textured model, textured template, by warping the former onto the later and measuring the color discrepancy. So these are some of the results we obtained. On the left, you have the input image. It works from just one image independently, of course. In the second column, you have the RGBD ground truth for this image. And in the third column, you have the results from our network in terms of the depth map with the error quantized. So as you can see, it's beneath 1 centimeter, even for quite complex objects like the dinosaur toy and the shoe. And on the right, you have the final output of our system, which is this as rigid as possible completion of the shape. So again, in the right column, we have access to the hidden parts of the object. So this is the strength of shape from template compared to things like monodepth, where you just have access to the visible part of the object and not to the hidden parts. So accessing the hidden parts of the object is extremely important in applications like computer-aided surgery, as you will see uh, in the application that I'll show at the end of the presentation. More results on this deep SFT work. Here you can see that even though we have trained our network with images from Kinect, we could apply the network with very good results from data from other cameras. So in the middle column, you can see a comparison to ground truth for another RGBD sensor, which has completely different intrinsic parameters compared to Kinect. And even worse on the right for the GoPro camera. More results, so it's quite resistant to changes in occlusions, illumination, and drastic changes in pose, deformation, as you can see on the right, changes in lighting as well. Here I have a short video, so it works in real time with frame rates, if I remember correctly, quite close to 15 to 20 hertz. So you can see the results is very resistant to occlusions. It produces a segmentation map of the objects at the same time as the reconstruction. It is on par with a physics-based system as the one that I've presented at the beginning with this juice bottle example. So last part in the presentation is the application we're developing in my group on the application of all these techniques to computer-aided surgery. And I'm going to speak specifically of the case of laparoscopy. So this is the case we started with. Nowadays, we also do other types of surgery, but this is, I think, the most simplest one to understand, because in laparoscopy, most people are familiar with endoscopy, and this is actually endoscopy in the abdominal cavity. So basically, they have this optics fiber with a camera, which is outside the patient body, and they make a small hole in the abdominal wall. So this is called a keyhole. And they introduce this camera and inflate the abdominal cavity with CO2 gas. So they create this working space. You can see an example of a patient on the right. And so they make several holes between 3 and 5 typically, where they introduce the camera. And the camera is here, by the way, and here you have a tool and another tool here. So typically there is an assistant who handles the camera, and the surgeon handles tools with their two hands, and there is an external screen, at least one screen. Typically there are 2 or 3 screens, and the whole staff in the operating theater can look at the inside of the patient together. So typically before this surgery, there is imagery, CT scan or MR scan of the patient to make the diagnosis, and the surgeon has access to this data. Either they remember it from before surgery, or they have access to it on a separate screen in the operating theater. Typically in this data, you can see what's going on inside the organ. So on the left, you have a slice of a CT scan of a liver. So that's the liver here, contoured in red. In this liver, there are two tumors, one in red here and one in green. And these tumors are endophytic. It means they're inside, really inside the organ. So that makes it a difficult case for the surgeon because when they have to remove these tumors, if you look at the right of the screen, this is what they see actually. This is the liver, same patient, and they have to remove these two small tumors, but they don't actually know where they are, and they cannot touch with their bare hands. In open surgery, they would touch and find the tumors because they're more stiff usually than the rest of the tissue. But in this case, they can't touch. So they can't really accurately find them. They have access to ultrasound, but this is full of artifacts. This is operator dependent, and the learning curve is very flat. So this is really a difficult case, especially on this particular patient I'm showing. So what we have proposed and worked on for the past decades is to actually bring this CT scan information directly into the endoscopy screen during surgery using a software that we have developed, which is called Hepatog. It means hepatic augmented reality in short, and that combines this preoperative CT and the intraoperative images. So this is loosely speaking the equation that we have to solve. The CT merge with the intraoperative image together to make a new intraoperative images augmented with internal structures like these two tumors in yellow here on the left and the vascular structures, which of course the surgeon has to spare during incision. So what we do to start with is a 3D reconstruction of the patient organ. This is quite straightforward. We segment the CT. Remember, the CT scan is a 3D volume, right? We have access to voxels. So if we segment and do some marching cube, we have access to a 3D model of the external part of the organ and the internal parts with the tumors, etc. Then our problem is to register the 3D model to the intraoperative images. And it looks exactly like this shape from template problem I have theoretically discussed in the past slides. The difference is we don't have texture in this case because the CT is not textured, of course. So we only discover the organ texture at surgery time. Nonetheless, we have access to some correspondences because there are some anatomical places that we can understand from the CT and the intraoperative images. So we still have access um, to correspondences, and from these correspondences, we have to figure out the shape of the organ seen from the of course the intraoperative configuration, because the organ deforms, as you can imagine, between the time where the scan is taken and the surgery, because the disease evolves, because the intra-abdominal pressure is changed, because the patient has moved, because the surgery tools will push on the organs and etc. So there are many reasons for the organ to deform. But believe me, it actually deforms quite a lot. And this is the registration process in action. Here you have this blue mesh, which represents the mesh from the preoperative data from the CT scan, which is fitted to the intraoperative image iteratively. And once it's fitted, we are able to apply this deformation field that we compute from the visible parts to the invisible parts, which are the ones we're really interested in, which are the tumors and the vessel tree. So now you can understand why it's so important in our application to not just recover the depth of the organ, but also the correspondence of what we see to this prior model, to this template, because this is from this correspondence that we will be able to transfer the parts that we don't see, which are either the hidden parts of the dinosaur tool I have shown, but in this application, that will be the parts which are inside the object, the tumors. So in this surgery, you can see this is our surgeon here. or hepatic surgeon in the surgery theater. And you can see the laparoscopy screens here, the ultrasound console, and our prototype here. So this was used on real patients, and as you can see, the surgeon started to incise here the organ to find the tumors, and we could measure post-operatively that the pieces of liver that were removed were, thanks to our guidance, really accurate. In this case, you must know that ultrasound didn't work to guide the surgeon because there were too many artifacts. So the surgeon was left blind, and without augmented reality, would have had to remove a much larger part of the liver to make sure that all the cancer part was removed, because these were two cancer tumors. And I'll leave you on this other video. So this is yet another application. So still laparoscopy, but this time on a uterus. And we here augment two tumors in yellow and the uterine cavity in black here with the tubes, which are so the parts that lead from the cavity to the fallopian tubes, which are very important to spare, of course, for these type of patients towards future pregnancy. So that ends my talk, and I'll be extremely happy to address questions, of course.
Thank you very much, Adrien. This is so impressive, this video and the talk, all of it, from taking us from fundamental structure from motion and up to the deep learning era and showing us this transition. This is very interesting and exciting. Thank you very much.
Thank you very much.
We have a small delay with the YouTube streaming, so we'll give maybe a chance for people to ask their questions on the chat, so please don't hesitate. In the meantime, I have a co-organizer who has joined, Anis Qasim. I also missed to introduce Mohammed Adel, our moderator today. So guys, feel free to ask questions. We have also Ksenia Cherenkova, who is the co-chair of SHARP. She's also online, I see. And we have Gerard, who joined already, Ponsmol, who joined already. Maybe I can start with a first question regarding this deep learning approach. As you said, it's trained for one known template, right? So for one object only. I was wondering if this condition can be relaxed, and if you have a template of a category of objects instead of one fixed object, if it would work or if there are adaptations to do.
Yep. Sure, that's a very good question, because being specific to just one object is, of course, a strong limitation in practice. So in order to generalize to a network able to cope with several objects at the same time, you have to consider two things. One thing is to be able to be generic to the shape of the object, so the geometry somehow, and the other one is to be able to be generic with respect to the appearance of the object, so the texture map. So we worked on the second aspect, and we have tried and managed to extend the system to handle objects of the same shape, but of different appearance. This is very recent work. We've just published it. So the paper is online, but I didn't have time to include the new results in the presentation. But this works almost as well as what I've presented for a single object. And basically what we did was to add a layer to the whole system that actually segments the object from the image. And the original contribution was to make an object segmenter that takes the input image, but also takes the texture map of the objects to segment as inputs, and is able to segment any object virtually given their texture map.
Mm-hmm. Now this is also very relevant for the SHARP workshop, because You probably saw the different data sets that we have. We have the same category, which is the body shape, but there's also variation. There's, of course, different proportions of a human body, and then you have different sizes, you have women, men, etc. So there's a variation there. It would be interesting to know which level of variation you're robust to in shape, but also in texture. In our sharp, we'll see that later during the workshop in sharp. So we have also variations in shape and appearance, and also in appearance, sorry, in texture. So we have naked or tight-fitting clothing. So mostly people are in sport clothing. So we have the same, very similar to the texture, the skin texture. And then we have variation, large variation in clothing. And of course, there are models for human bodies, simple. I think that Gérard will talk about that, etc. So how can this be adapted to these existing models, and to which extent do we have robustness with respect to variation in shape and variation in appearance?
That's a very good question as well, and we haven't tried to, I mean, on humans yet, but I think we should at some point, and I think definitely there's an overlap between human-centered methods, human-specific methods, and the methods we developed, which are also applied to human eventually, but not on people, on photo of people, but on photo of internal organs. And then that's quite a different setting, though I think most of the blocks can be reused and taken inspiration from in developing these methods. So far, we're quite robust to variations in geometry, and we're actually working on what we've called weak prior NRSFM, where we're able to use a very generic prior. So you can imagine that rather than having the exact shape of the organ or of the object of interest, we have a generic shape. Like for this organ here, we could have a shape which would be just a sphere. And so that provides a very weak knowledge, mostly actually the topology of the objects. And our goal is to use this very weak prior to improve non-rigid structural motion. And we have started to work very actively on that. And our first results are very encouraging.
That's very exciting, and I look forward to see more of those results. I see here a couple of questions on the chat, so I'll read them out loud here. So you have from Devesh, hi Adrien, very interesting research and application indeed. Could you say a few words about your recent IGCV work on the isowarp? Its context within your talk, an analogy with rigid multiple view geometry.
Sure.
This is a fan.
I'm moving back actually because this is something I have skipped, but which was in the presentation. So just give me a second. Oops. I'm just moving to the right place where this. Yes. It seems screen sharing stopped, right? So I have to share again. Can you see my screen?
Yes, we can.
Yeah, okay, excellent. So this is indeed the slide I skipped, and I think it's a very fundamental question. The question, if I understand correctly, I think I do because it was really clear, is if we're given two images of a surface that deforms isometrically, do we have geometry constraints on the optical flow, on how the first image deforms to the second one? And the answer is yes, and that's actually the contribution we have published in this IGCV paper that the question's referring to. So we have found that this function here, which is written eta, that maps pixels from the template to the input image, is actually not any arbitrary function. This function is constrained by a second order differential constraint, which must be fulfilled in order for this function, this warp function, to be a valid representation of the underlying world 3D structure projected to images. In perhaps simpler terms, you can imagine that when you take two photos of a rigid object, these two photos are related by the fundamental matrix. If they are not related by a fundamental matrix, it means they are not valid observations of a 3D structure. Period. That's geometry. So you can see these constraints we have formulated on the warp as an extension of this theory to the case of an object, of a surface, which deforms isometrically. And we have shown that the constraint, of course, is much more complex than the fundamental matrix, but in the end, obeys a second order PDE constraints, which is not that complex. Importantly, this is valid when you have a template. In the case where you would just have two photos of an object without a template, we have started to study this new case. It's more involved. We don't have the answer yet. We don't know if there will be a simple constraint to exploit. My guess is that there'll be one, but we'll need at least 3 images to formulate it. But algebraically, it's a more complex case, and we're looking into it.
Thank you, Adrien. There's one more general question also here in the chat, and then we'll take maybe one more here and then move to the next one. So you mentioned 2 approaches, the handcrafted and deep learning. What could be a third approach?
That's a good question. I suppose that there's a third one which we haven't invented yet. By we, I mean the whole scientific community, of course. But I suppose these days something extremely worthwhile is to combine learning and physics-based models. Of course, is proven in numerous problems to be extremely effective. And as far as I can tell, in our approaches, in this deep SFT approach, we have a physics-based block at the very end, which is extremely fast and effective, simply because this is a subpart of the problem where we have physics-based constraints. They are simple to solve. There are efficient algorithms for that, and somehow there's no need for training. So why training a machine to approximate a complex function in the cases where we can solve it simply with an algorithm? So I suppose this is the answer.
This maybe leads to my last question, at least, is about the acceptance by the medical community and surgeons to use data-driven approaches, deep learning approaches in their surgeries. Well, you said if you have a good fundamental model, you probably don't need that. I'll let you answer.
Well, we actually do need some deep learning in the pipeline. So in the results I've shown, there's no deep learning so far. But our next step is, I mean, we have developed an improved method that embeds some deep learning, and that actually improves some parts of the pipeline. And again, that's a combination of deep learning and non-deep learning bits. But on the acceptance of AI in general and deep learning in particular by the surgeons, there is absolutely no problem. They're very enthusiastic with this. I suppose it comes from, of course, the hype of it, because they can read about it, they can see about it in the medias, but also because they really believe it will improve healthcare. it will make their lives easier in several parts. So for instance, in the systems we develop, we have to prepare this preoperative model by segmenting CT or MR. So at the moment, we do it by hand, and we take help from a radiologist or one of the surgeons. And it's a bit of a painful process. It's not very interesting. It's time consuming, and that's typically something that we aided a lot in deployment. So that's the type of things they see when I say making their lives simpler. So,
Thank you very much, Adrien. Maybe with that, we conclude your talk. Thank you so much. Very
thank you for the
fascinating work
invitation.
and application. C'est
Thank you.
if you